Hello everyone, and welcome to another RTDS Technologies webinar. My name is Katie Sidwell, and I'm Technical Marketing Manager at RTDS Technologies, and I'm happy to be hosting and moderating today as we discuss real-time simulation with NovaCor Light, a lightweight alternative for heavyweight innovation. So this is a little bit different than our normal, more applications-focused webinars. Today, we're really going to be zooming in on this newer product offering of ours, which is a lighter weight alternative to our flagship NovaCor hardware, geared more at entry-level users. Our webinar format, however, will remain exactly the same, so you are encouraged to ask questions throughout the webinar by submitting them via text in the Q&A widget. So try not to use the chat widget for questions. Using the Q&A really helps us keep track of your questions. And then we will be answering those throughout the webinar and then discussing a few of them in the live Q&A right afterward. And not to worry, this webinar is being recorded and it will be published on our YouTube channel and can be watched freely that way. Also, if you have any colleagues who missed it, they can register to view the webinar on demand on our website. So these materials are not going anywhere. All right. There will be about 45 minutes of content today before we go to the live Q&A period. I'm going to start by talking very briefly about real-time simulation fundamentals and focus a little bit on what we do differently at RTDS Technologies with the RTDS Simulator. Then I will give an overview of NovaCor Light, what it looks like from a hardware perspective and a software perspective, as well as some information on the pricing structure. I'll give a quick overview of simulation capabilities, and then I will turn it over to my colleague Christian, who will give a demonstration in the RSCAD FX software, showing some of the cases that can be run with NovaCor Light. The simulations you'll see today are electromagnetic transient, or EMT, power system simulations, which are running in real time on our dedicated parallel processing hardware. And EMT simulation is much more granular and allows for a much greater depth of analysis than traditional phasor domain representations of the power system. So we're seeing a great uptake of EMT simulation by utilities and system operators, where they would ordinarily use an RMS or positive sequence only representation of the power system. And that's because there is wide recognition of the fact that EMT simulation is critical for capturing fast network dynamics during transient conditions and accurately representing fast-acting controls of inverter-based resources, which more and more have a dominant effect on our power system dynamics. So EMT simulation, whether that's using the RTDS Simulator or an offline EMT simulation software like PSCAD, is a critical part of the modern power engineer's toolbox. And running these EMT simulations on dedicated parallel processing hardware instead of a regular PC is what allows us to sustain real-time operation, and in turn, that is what enables hardware in the loop, or HIL testing. HIL testing is true closed-loop testing. So we are continuously maintaining hard real time. We have the option to bring data outside of the simulation into the real world, whether that is through conventional analog and digital I/O or communication protocols. Apply those signals to an external device under test, whether that's a protection relay or a controller, and then bring back the response of that device into the simulation. Doing this requires very high fidelity computing and I/O, as well as highly accurate power system component models. So that's what we do at RTDS Technologies in developing the hardware and software components of the RTDS Simulator for HIL testing. Hardware in the loop testing, or closed loop testing, is differentiated from open loop testing in that the test continues after the action of the device under test. So not only are we seeing that controlled or protection device respond, but we're also seeing the dynamic response of the network. And inherently, this means we can also test multiple devices simultaneously to see how different systems and schemes are interacting. So take a modern microgrid, for example. Here we have different tiers and functions of control and protection that need to all interoperate seamlessly in order to have a secure and resilient microgrid. So with a real-time simulator, sure, we can test those control and protection components individually, but we can also have the secondary master microgrid controller, the primary device level controls, and the more tertiary higher level SCADA controls all together in the closed loop testing environment. This is getting to as close as it gets to field testing in terms of the level of accuracy, but we're in the safety and flexibility of a lab environment. So we can introduce different system conditions that would be impossible or impractical to do in the field to this equipment in the lab. So RTDS Technologies is based in Winnipeg, Canada, and we pioneered real-time digital power system simulation back in the 1980s. Originally, the RTDS Simulator was developed for testing HVDC controls here in Manitoba. Today, we have customers in over 57 countries around the world. Primarily, we work with utilities, manufacturers of protection and control equipment, universities and research institutions, as well as some power system consultants. Something we do uniquely at RTDS is the in-house custom approach to the integration and development of our hardware and software. So our hardware and software components are developed specifically for the real-time power system simulation application. For example, on our hardware, there's no operating system running underneath our executable code on the hardware. So that gives us the best possible performance. And it also gives us a high level of control and knowledge of our product. We don't use off-the-shelf hardware or any third-party software products. So that really allows us to comprehensively support our users and help them complete their projects. And it also means that there are fewer issues when it comes to compatibility. We're truly proud of and we stand by the high quality of our product. And we're committed to equipping users to doing good work with the technology. And that's one of the reasons why we remain the industry standard in real-time simulation. So the RTDS Simulator is used by all of the leading protection and control manufacturers and many major utilities as well. One example of how embedded this technology has become in the power industry is that it's frequently specified as part of major HVDC projects. So both from the HVDC control manufacturer side, this tool is used for testing the controls prior to delivery, and also from the operations side. The utility that is responsible for operating the link will often receive a set of replica controls that's connected to an RTDS simulator for pre-commissioning and ongoing testing as well. So using this tool is a great opportunity for students to get transferable experience. We have a lot of examples of students going to work in real-time simulation labs in industry or work alongside those industrial partners with their tool of choice, with the RTDS. And with that, I'm happy to get into some details on NovaCor Light. So you might have already read a bit about this product on our website or maybe seen our video about it. And it's important to understand that this is a lighter weight alternative to our flagship product, NovaCor 2.0. This is a little different than a whole new hardware generation. It doesn't have any major feature or performance advantages over our flagship hardware. In fact, it's a lighter weight version, so it's more geared toward entry-level users, and it's a more accessible way in to world-class real-time simulation. The form factor, if you're familiar with NovaCor 2.0, is exactly the same. So it's a 4U tall, 19-inch wide unit. It's rack mountable, but it can also be used tabletop. And it's based on a multi-core processor with 4 available cores. So this is a major difference. Our NovaCor 2.0 hardware is based on a multi-core processor with 10 cores, and here we have 4. NovaCor Light also has some built-in I/O, so it basically includes what you need to get started with basic hardware in the loop testing. And you'll notice another difference is that there is no front touchscreen on NovaCor Light. It's a simpler chassis. Here we have a look at the connectors for our built-in I/O that's in the box. So on the left, we have our 32 digital inputs and 32 digital outputs. And on the right, we have 12 analog input channels and 12 analog output channels. We also provide these terminal blocks that are shown on the right for easy connection to external equipment. So those are very similar to what you would see on our existing modular GTIO cards. NovaCor Light also maintains the UDP port that is existing on NovaCor 2.0. So that's an RJ45 port that can be used for direct connection via UDP to external applications or devices. And that can be used for large data logging or for co-simulation with PSCAD as well. The fiber ports at the bottom of the chassis rear have very similar functionalities to our existing NovaCor series, just with slightly smaller numbers. So 4 of those fiber ports are available for connecting additional I/O cards. So you're definitely not limited to the built-in I/O. You can daisy chain our analog and digital input and output cards from a single fiber port. So in theory, you could have many I/O cards connected to one NovaCor Light chassis. Additionally, 2 of the fiber ports are reserved and can be optionally licensed for the Aurora communication protocol. So that can be used to directly connect NovaCor Light to Aurora-compatible 4-quadrant amplifiers for power hardware in the loop testing or other devices. I really want to emphasize that NovaCor Light is compatible with all of our current generation I/O and peripherals or auxiliary hardware. So there's no real limit on the HIL applications of NovaCor Light because it is compatible with all of these cards. So the ones shown on this slide are our analog and digital input and output cards. We do have the built-in channels, but those capabilities can be expanded by purchasing additional cards. And then we also have our communication-based I/O. So on the left side of this slide is our GTNet X2 card. And this can be used for standard compliant Ethernet-based communication, whether that is IEC 61850, sampled values and Goose communication, DNP3 or IEC 6870-5-104, Modbus, TCP or UDP generic socket communication, or synchrophaser data. So lots of applications of that GTNet card. And then we also have our GTSOC V2, which is compatible with NovaCor Light. So that's used for special applications, including black box control integration, which we did a recent webinar deep dive on, as well as MMC HVDC simulation, which we will be doing a deep dive on in June. Make sure to sign up for that webinar if you haven't yet. So these are connected to the rear of the NovaCor Light with fiber cables, just as they would be with our regular hardware. And of course, it's also possible to expand the system by connecting to other units. So the basic form of scalability with this product is through core licensing. You can purchase the NovaCor Light chassis with 1 licensed core and then license additional cores as your simulation requirements increase. But it can also be connected to not only other NovaCor Light units, but also NovaCor 1.0 or 2.0 units. There are 3 fiber ports reserved for this on the rear of the NovaCor Light, so that means in total 4 units can be directly interconnected with fiber cables. We also have our regular global bus hub and IRC switch, which allow for scaling beyond this direct interconnection level. So those hubs can be used to expand considerably and have many, many units participating in a simulation. Just keep in mind that whenever you're connecting multiple chassis together, whether that's NovaCor Light, NovaCor 1.0 or 2.0, there will be a subsystem split. So the simulation will be decoupled using a traveling wave interface between those units. So that's the NovaCor Light hardware at a glance. Again, it's the same hardware philosophy and architecture as our existing NovaCor series, but we have 4 available cores for licensing instead of 10. And the capabilities of each core are also different, which I will explain shortly. In addition to that, we have our built-in I/O. We have fiber ports reserved for I/O card connections of any type, fiber ports reserved for expanding the simulation by connecting to other units, a UDP port, and of course our Ethernet port to connect to the LAN or the user's PC. So what does NovaCor Light look like from a software perspective? Well, it integrates with RSCAD FX, which is the same software that is used with our flagship product. So there are no differences from a graphical user interface standpoint. It includes all existing modules and features, so there's no limit to the libraries that can be used or the types of applications that can be pursued with NovaCor Light. You get the exact same software package as someone using NovaCor 2.0 would get. As always, RSCAD FX is distributed via site license, so when you purchase the software, it can be installed on an unlimited number of PCs on site. And there's no third-party modules. So RTDS Technologies develops, maintains, and supports this whole software package in-house. I also wanted to mention a couple of the component models that differentiate us. So RSCAD has the most robust and detailed library of real-time power system models on the market. And one of the reasons for that is that our development is pushed by some of our leading users. So if we have a manufacturer that wants to test traveling wave protection, we need to develop the models so that they can do so. One of our most interesting and in-demand components is our Universal Converter Model, or UCM. So this is our main power electronics model. It's available for a variety of fixed converter topologies. And what makes it compelling is that it enables multiple switching instances within a single time step. So we're able to support much higher frequency for PWM without driving that time step down and really clogging up our simulation hardware. So it's a relatively lightweight but still powerful and detailed model that can represent anywhere from a few kilohertz to the 200 kilohertz switching range. And for lower frequencies, it can be placed in our main time step environment, which is really interesting for users with smaller simulator configurations. We also have a faulted phase domain synchronous machine model that can be used for 100% stator to ground fault testing, and some of the most detailed modular multi-level converter models on the market. I won't get into detail on those today, but if you have any questions, please feel free to ask. Before I pass it over to Christian for a demo, I'm going to touch briefly on the simulation capabilities of NovaCor Light. And by that, I mean the size and complexity of networks that this platform can simulate. I want to stress here that when you're looking at real-time simulator capabilities, it should really go beyond just quantity of nodes. So we're going to show you some sample circuits today, and in general, we like to provide sample circuits to those interested in our technology that show the complexity of power system that can be represented. So it's important to have more than just passive networks between each node, right? We need to represent complex components like machines and transformers and inverters. So when we specify networks, we assume that it's, a detailed populated network, not just a passive one. It's also important to note embedded nodes. So on some components, like the machine that's on this slide, also on source models and transmission line models, we have some nodes that are embedded in the model itself that aren't solved by the network solution. So this can effectively increase the size of network that you can represent on RTDS simulator hardware. The machine model here includes an embedded unit transformer and breaker nodes as well. And finally, anytime we're talking about node limits here, we are talking about tightly coupled nodes. So if we mention a maximum node number, that is in one tightly coupled network solution. There's no subsystem splitting involved, which then introduces a traveling wave interface, which can add some shunt capacitance to the system. So tightly coupled networks that assume some complexity. Our most basic configuration of NovaCor Light will have a single licensed core. And with a single core, we are stacking our network solution, power system, and control components all together on the one core. When this happens, we can accommodate a maximum of 54 single-phase power system nodes. Once we introduce multiple cores, Then we dedicate a single core to the network solution, while other cores handle components in parallel. So when we have more than one core licensed, we can accommodate a maximum of 180 single-phase nodes. And moving from 2 cores to 3 cores to 4 cores will simply increase the complexity of the network that can be modeled. So if you're familiar with how we do hardware allocation on the RTDS simulator, basically you're getting additional load units. So you can have more inverters, more generators, transformers, and lines in your network of 180 single-phase nodes. Christian will go into much more detail on the types of cases we can run on a single core and a 4-core NovaCor Light. But here's an example of a network that would run with 2 licensed cores. One of the nice things about the universal converter model is that it's so lightweight. So you can place it in the main time step environment and it only requires 10 load units. And that means that folks with a single core licensed on NovaCor Light can still have detailed power electronics simulation in the 10 kilohertz switching range. However, our substep environment is available for NovaCor Light as well. So with substep, we're dedicating a single core to typically a power electronics subnetwork with a time step of less than 10 microseconds. And when we do this on NovaCor Light, each subnetwork can handle 36 single-phase nodes. So for folks who are interested in switching details for converters above 10 kilohertz up into the 200 kilohertz range, this is a great option. And this can be run standalone on a single core NovaCor Light as well, or you can run a multi-rate simulation if you have more cores available. Distribution mode is also available for NovaCor Light. So here we get higher node counts, assuming a radial feeder structure, so a more sparse admittance matrix to effectively invert every time step, and also a slightly higher time step, so a minimum time step of 100 microseconds instead of the typical time step of 25 to 50 microseconds. So with distribution mode, a single core NovaCor Light can solve 375 nodes or 750 nodes with multiple cores. All right, touching briefly on our pricing model. When you purchase a core license for NovaCor Light or for our products in general, you have purchased that license outright. So we don't charge ongoing core licensing fees. We do have an optional but recommended annual hardware warranty fee for repair and replacement with no deductible, but we try to keep those fees relatively low. Also, educational institutions receive perpetual software maintenance free of charge for non-commercial use. So that means that if you're a learning institution, you always have access to the most up-to-date software, our bug fixes, our new releases, and you have access to our simulation support team. And that is perpetual for the lifetime of the simulator at no cost. Commercial users do have the option of paying for this ongoing software warranty and maintenance, but again, we try to keep our fees relatively low. If you have further questions about specific pricing, please reach out to us directly, as we won't be discussing that much in the Q&A. I've put our sales email address here, or you can head to our website and fill out our contact form if you'd like more information. Finally, our training and learning opportunities. We have an online video resource library that is available always free of charge for users. And that includes software tutorials, getting you up and running from zero experience with our software. Also, hardware tutorials, some sample hardware in the loop testing videos, so you can get experience with using our I/O to connect external devices. We also do a lot of webinars, but you knew that because you're here. And we have a very active community of users who we connect through our regular users group meetings. So we do UGMs in a few different areas around the world, either annually or biannually, and our online knowledge base actually includes most of the presentations from those meetings. So if you're curious what other people are doing with this technology, we try to make that information as accessible as possible. Thank you so much for your attention in this part of the presentation. And now I'm handing it over to Christian for our demo.
My name is Christian Jaggs, and I'm one of the engineers at RTDS Technologies. In the demo cases that we have prepared for today's webinar, we have two demo cases to show you. One is a multi-core demo case, and the other is a single-core demo case. Now, the multi-core demo case uses all 4 cores of the NovaCor Light and will demonstrate the simulation of an industrial microgrid system. In the single-core demo case, we use a single core of the NovaCor Light to demonstrate a Type 4 wind farm with ride-through controls. Let's have a brief introduction into the demo cases. First, with the multi-core demo case, the microgrid model that we're going to be simulating is known as the Banshee microgrid. This microgrid is based on an industrial facility with 3 radial feeders, which are broken down into 3 separate areas. Area 1 on the left, Area 2 in the middle, and Area 3 on the right. Each area has its own generation assets, either renewable energy-based generation, such as PV or battery energy storage, or other types of generation, such as diesel generation, or combined heat and power-based generation. Each area has its own generation assets and its own loads. Each of the loads have their own priorities associated with them as well. Some loads are considered critical, other loads priority, and other loads interruptible. The renewable energy-based generation is interconnected to the microgrid by using inverters. These IBR-based resources are modeled using detailed switching models with our universal converter model by using the improved firing algorithm. Now, some minor modifications did have to be made to the Banshee microgrid model in order to fit it into the 4 cores of the NovaCor Light. These modifications simply required us to remove a couple breakers as well as transformers. But the single line diagram you see on the screen here is representative of the system being simulated in the demonstration. Next, for the single core demo case, we're going to be simulating a Type 4 wind farm with ride-through controls. We can see a single line diagram of the system here. In this system, we have an AC source representing the grid that's connected through 2 transformers to our Type 4 wind farm. We have 2 converters connected back to back. One is designated the grid side converter, the other being the machine side converter. These 2 converters connect to a permanent magnet synchronous machine, which is then connected to our wind turbine. You'll note that transformer 1 is being modeled as a scaling transformer, which allows us to scale up the power from this wind farm. The controls in this example case include sequence components controls, which also include functionalities such as low voltage ride-through and high voltage ride-through. Okay, with that, let's jump into RSCAD FX and have a look at the demo cases. Now let's have a look at some of the different models for the demo portion of today's webinar. As I mentioned previously, we have 2 demonstrations for you today, a multi-core demonstration and a single core demonstration. Let's start with the multi-core demonstration. In the multi-core demonstration, we're going to be using all 4 cores of the NovaCor Light to simulate a microgrid system. This microgrid is known as the Banshee microgrid, and it's broken down into 3 separate areas. Area 1 on the left, Area 2 in the middle, and Area 3 on the right. Now, each one of these areas has its own generation assets as well as loads. So let's go ahead and have a look at some of the details of the model, starting with Area 1. So if we zoom in here, we can see the head of the feeder for Area 1. We can see some breakers that are used to interconnect to downstream buses where we have transformers which lower the voltage level. We also see that we have some dynamic loads which are connected at these buses. If we scroll down further, we can see we even have some motor load being modeled here using our induction machine component. So those are some of the loads in Area 1. Let's have a look at some of the generation assets as well. So Area 1 has a diesel generator, and this is being modeled using our synchronous machine component. This component also interacts with our governor and exciter controls. Moving on to area 2, this is the head of the feeder for area 2. We can again see some breakers connecting to buses downstream. Now area 2 is where we have our inverter-based generation, both PV and battery energy storage. Let's go ahead and look at how this inverter-based generation is modeled, starting with the PV system. So if I open this up, we can see the model of the PV system. So we have an inverter here, and the DC side of the inverter is supplied from our PV array component. Now this inverter is a detailed switching model using our universal converter model with the improved firing input. This allows the inverter's transient behavior to be modeled up to the range of 15 kilohertz. So included in this inverter are some typical controls that are used in these kind of PV systems: an outer loop control for voltage control, maximum power point tracking, as well as inner current control loops. These controls generate a set of modulation waveforms, which are then used in our firing pulse generator component. These modulation waveforms are compared against a carrier waveform, and we use this to generate firing pulses to fire the switches. Now let's have a look at the battery energy storage model. The battery energy storage model is very similar to the PV model, except the DC side of the converter here is being supplied by batteries. In the battery storage model, the controls have different functionalities or different modes of operation. The battery energy storage system can operate in a grid following mode, or can also operate in a grid forming mode. This grid forming mode is used when area 2 is islanded from the rest of the microgrid. Now another thing to note is that these universal converter models are operating in our main step environment. You can see right now the size of the main step is 30 microseconds. So despite having a simulation time step of this size, we're still able to model frequency components up to the range of 15 kilohertz with these universal converter models by using our improved firing algorithm. Okay, so that's some of the generation assets in area 2. You'll also see we have other loads, dynamic loads in this area as well. We can also see that there's connections between the two areas and area 2 and 3 as well. Now moving on to area 3. Area 3 is very similar to area 1. This is the head of the feeder here. Again, we're connecting to downstream buses through breakers. The generation in area 3 is our combined heat and power base generation, which is modeled using a synchronous machine and associated exciter and governor controls. We also have some more dynamic loads and motor load here being modeled using an induction machine. So with that, let's go ahead and now compile the model. So before we do that, let's have a look at the case settings. So I can see the simulation time step for the main step is set to 30 microseconds. And if I want to compile the model, I can click this button here. So I've compiled the model using a 30 microsecond time step. If I want to change the time step, I can easily do that. I can say change it to 25 microseconds, and I can recompile the model. You can see that it recompiles very quickly. Now let's go ahead and look at how this model is assigned to the various cores of the NovaCor Light. So this processor assignment chart shows me how that works. So we can see that core 1 is handling the network solution. This is responsible for solving all the node voltages throughout the network. Cores 2, 3, and 4 are handling all of the various power system components throughout the microgrid model. You can see that some of these components take up more space on the core, and some components take up less. On all 4 of these cores, you can see that we've split up all the controls and stacked them onto each of the cores. Okay, with that, let's now move on to the runtime environment and run the model on the NovaCor Light. Okay, this is the runtime environment for our multi-core example. Here you can see we have a graphic showing a single line diagram of the microgrid, And on top of this graphic, we've overlaid various different components such as meters, push buttons, and icons for the breakers. The colors of these breakers will change as the breakers change status. If we want to run the simulation on the NovaCor Light, we could do that by pushing the Run button up here. What this does is send the previously compiled files to the NovaCor Light hardware, and the hardware then begins running the model in real time. We can then interact with the model through this runtime environment. So the case is now running. We can see some of the graphs, as well as some of these meters here, are now updating. So we can see some of the power flows, as well as bus voltages at the different buses. Now recall that in Area 2 is where we have our inverter-based generation. Since Area 2 is grid connected, the battery is currently operating in a grid following mode. If we want, we can island Area 2 by tripping the breaker at the head of the feeder. Let's do that now. We see that once we island Area 2, the battery switches from a grid following mode of operation to a grid forming mode of operation, as the battery is responsible for controlling the voltage and frequency of the island in Area 2. This allows the PV to continue to operate. On this phasor diagram here, we can see the mismatch in the frequency between the island and the grid. The battery is controlling the frequency of the island to around 59.8 Hz. If we want, we can go into the frequency controls of the battery and adjust the set point. Let's increase it to 59.9 Hz. We can see that change here. If we want to reconnect the island to the grid, we can push this close button here. However, the breaker won't close until the synchronization criteria is met. So once these phasors become aligned with each other, we can see that the breaker recloses and that the battery reverts back to the grid following mode of operation. If we have a look at some of the voltages throughout the network, we can see some of the switching harmonics that are on the waveforms since we modeled the converters using detailed switching models with our universal converter model with the improved firing in the main step. That concludes the demonstration. I'll go ahead and stop the case now, and let's move on to the single core demo. Okay, now let's have a look at the single core example for the NovaCor Light. In this example, we're going to be modeling a Type 4 wind farm. Let's have a quick overview of the model. You can see that we have an equivalent here representing the rest of the AC system that's modeled using this voltage source and this impedance here. After that, we have a fault branch that we can use to impose faults on this system, followed by a breaker. This breaker is then connected to our scaling transformer here. This transformer allows you to scale the power up from the wind turbine to make it look like multiple wind turbines are injecting power. On the other side of the transformer, we can see that these nodes here connect into this hierarchy box, which is used to model the wind turbine. Let's open up this hierarchy box and have a look at the remainder of the circuit inside. If we open this hierarchy box up, we can see that those nodes on the hierarchy box connect over here into another transformer. This transformer then connects to a breaker to the back-to-back converters, which connect to our permanent magnet synchronous machine, which is used for the wind turbine. The wind turbine model is inside this hierarchy box here. This wind turbine model interacts with the electric machine model here. Now, similar to our previous example, the converters in this example are modeled using our universal converter model with the improved firing algorithm in the main step environment. These are detailed switching models that will allow us to simulate frequency components up to 15 kHz. You can see we have two converters being modeled here. This converter over here is known as the grid side converter, while this converter over here is known as the rotor side converter. Now, we've included various controls in this simulation case. And these controls include various functions such as low voltage ride-through, high voltage ride-through. And the controls operate using sequencing components. That is the positive and negative sequence components of the voltage and current. The details of those controls are included in these hierarchy blocks here. You can refer to the documentation for more details. With that, let's close the hierarchy box and let's compile this on our single core NovaCor Light. Before we do that, let's have a look at the case settings. We can see right now the simulation time step is set to 25 microseconds. If I compile the case, you can see it compiles quite quickly. If I want, I can even reduce this time step further, say to 20 microseconds. Again, the case compiles quite quickly. Now that the case is compiled, let's have a look at the processor assignment chart to see how the various components are stacked onto a single core of the NovaCor Light. This chart here shows the stacking. We can see that the controls, network solution, and various power system components are all stacked onto a single core. You can see that the single core is almost completely full. Okay, with that, let's move on to the runtime environment and run this model on the NovaCor Light. Okay, this is the runtime environment for the single core demo. Here you can see we have a single line diagram of our wind farm system shown on the canvas here. Again, we've overlaid various icons for the breakers and different components such as push buttons, switches, or sliders. If we want to run the simulation model on the NovaCor, we can do that by clicking the Run button at the top here. Again, this sends the previously compiled files to the NovaCor Light hardware, and we'll run this system using a single core of the NovaCor Light. The system is running in real time now, but all the breakers are open and we haven't wrapped up the AC voltage of our source. So we can do that by pushing the Start button here. Once we push the Start button, the voltage of the AC source will ramp up, and the breakers will close, and this will energize that portion of the system. However, the converters are still blocked, and we haven't deblocked them yet to start operating the converters. So we can do that next by clicking this deblock button here. Once we click the button, we've successfully deblocked both of the converters, and now the controls are fully functional and the system is operating. We can see we have about 2.5 megawatts of power coming from our wind turbine. It's being passed through the converters, then passed through our scaling transformer. You can see the scaling factor here is a factor of 100, so the power is scaled by a factor of 100. Next, what we can do is apply a fault at this point here. Then we can observe the low voltage ride through in this example. The controls for the fault are set using these sliders here. We can simply click this push button to apply the fault. So let's do that now. Once we push the button, the fault is applied and the plots will automatically update to show us the results. Okay, the plots have finished updating, so let's have a look at the results. We can see that during the fault period, the voltage is reduced. This low voltage condition is then detected, and this low voltage flag is set. Once the low voltage flag is set, what we can see is that the active power of the system is actually brought to 0. We can see that here. So the control detects the low voltage condition and sets the D-axis current reference to bring the power to 0. It also adjusts the Q-axis current reference. We can see that adjustment here. After the low voltage condition is finished, the current is then smoothly transferred back to its pre-fault condition. Okay, that's all I wanted to show in this single core example. So let's go ahead and stop the case, and that'll conclude today's demonstration for the webinar.
Okay, thank you so much everyone for your attention and your attendance today. we have a few questions that we will chat about before we close for the day. So we had a question about how many NovaCor Light chassis can be used together for co-simulation. And I think we covered that in the presentation, but just to expand a little bit, there's kind of two aspects to connecting multiple RTDS simulator units. There's both the data side and the time step distribution side. So the NovaCor Light has the capability of communicating directly with up to 4 chassis via IRC. So that's from the data side, using fiber ports that are dedicated to that on the rear of the chassis. But then you also have to think about the time step. So you can directly connect 2 units together using our GBH cable to distribute the time step. But if you want more than 2 units in the same simulation, you need a piece of hardware called the Global Bus Hub to accommodate that. But theoretically, you can connect up to 144 units total if you're using both the Global Bus Hub for time step and the IRC switch for data. So there's a considerable amount of units that can be fully interconnected. Okay, let's talk a little bit about capabilities, specifically about nodes. We have a question on the maximum of single phase nodes per chassis and whether the core in the single phase example has been used with its full capability. So I have my colleague Cyprian Peters from Technical Sales with me. Cip, do you want to comment on these questions?
Yep, sure. So as was mentioned, a one core simulation, if you're only using one core of NovaCor Light, the maximum number of nodes is 54. If you're using more than one node or one core, you can have up to 180 single phase nodes. One thing I want to mention is that often a simulation size is when people ask about the size of a simulation, they ask about number of nodes, but we need to consider a little bit more when it comes to real-time simulation, and that is the components that are in a network. So our goal is to run the simulation at 50 microseconds or less in real time. That's our target for typical EMT simulations. And in order to do that, we consider the components in the network, not just the nodes. So we have things like machines and transmission lines and transformers. And what we've done in order to ensure that the time step meets the 50 microsecond requirement is we've come up with the load unit system on the cores. So a certain amount of the one core simulation is required for the network solution and the nodes, and the rest of that core you can stack power system components on, so those machines and transformers and transmission lines. And the way to size the network is to know how many of those components are present in the network and how many load units that you have on each core. So that's always something to consider for real-time simulation. The single core network that was demonstrated on the webinar was 27 out of 54 single phase nodes. And you'll see it's not coming close to the maximum amount of nodes that are allowed, but the power system components that are present there actually fill up the core mostly to its full capacity. There was a question about whether GTFPI and LV and HV panels can be used, and the answer is yes. We have a portable I/O cubicle that's just a little cubicle with power supplies in it and a couple DIN rails, and 4 to 6 I/O cards can be put in there, external I/O cards. So if you need additional I/O to what is present inside of NovaCor Light, you can put those cards in there. And the front of that portable I/O cubicle can actually house an LV and an HV panel as well. So you can put the GTFPI card on the DIN rail inside the portable I/O and have access to the LV and HV panels on the front of the portable I/O cubicle. Another question on checking the number of nodes. Essentially, you need to compile your circuit, and then there's a file that you're able to look at that tells you how many nodes are present in the circuit. One of the answers to another question there was that we have some documentation on how many cores are required for some sample systems, and that documentation will also help to show you how many nodes that we are counting in a system. And one other thing to mention is that the way we count nodes is a little different from how other softwares sometimes count nodes. So nodes for us are basically nodes between different components. And we do a lot of embedding of nodes in our simulations. We're able to embed breakers and even transformers in our machine models. So that actually saves you quite a few nodes. And if you were to count those nodes, the number of nodes in the system actually ends up being quite a bit more than we are actually counting for our network solution. And I see one other question here about digital inputs and improved firing. And yes, that's correct. The improved firing is supported with the digital inputs provided in NovaCor Light.
Thank you, Cyprian. Yeah, we had another question about the built-in I/O as well, and the specs of that I/O, like the capabilities, are the same as what you would see on our traditional I/O cards. So, yeah, it does support the 10 nanosecond sampling for the UCM. Okay, I think that wraps up our questions. So thank you everyone again for joining. Thank you to my colleagues Christian and Cyprian for their involvement. And once we close this webinar, you will be directed to a sign-up page for our next one coming up next month, which is focused on offshore wind integrated via MMC HVDC. So there's a wind aspect and an MMC converter simulation aspect to show off some of our new models. So highly recommend registering for that one. And we'll see you all next month. Thanks, everyone.